So I just repeated Erdős-Corrado theorem, and I started the second proof with a lemma. So now we have a ordering of the elements from 1 to n along, say, the cycle, and G is a family of intervals of length k. Again, it is less than n half, less than equal n half, and that and intersecting. So we just mimic Erdős-Corrado theorem for this structure, and I proved actually that the family cannot have more than k elements. So we proved this at the very end. And using this, I want to prove the Erdős-Corrado theorem. Double counting C and F, where C is a cyclic permutation of n. So here I made this order 1, 2, 3, but now we will take all possible ordering. So mix them. 177, 82, and so on. So this is an element of C. F is in the family, the intersecting family from the theorem. Interval in C. Maybe it's not clever to write a script letter, but I hope you don't mind. So this is one ordering, and F is taken from the family. So imagine that we mix the elements, the members of F, and some of them become intervals here. Some of them don't. So at this moment, we just consider those which become intervals in this cyclic ordering. And double counting means that we fix one side and then fix the other side. So try first with fixing F. So it is a member of the original family. Oh, so it's one of them. Yeah, so it's one of the intersecting families. And now we try to mix the elements in a cyclic way and So we know that the number of f is just a notation. So this is the size of the family, and for each such set, we have to determine in how many times we can order, how many cyclic orderings we can have where f is an interval. So if f is an interval, then and this is the rest. So how many ways we can put here the elements? Since this is cyclic, it doesn't matter where we put f. But so if we want to have f as an interval, then we can mix only these elements. In how many ways? Of course, k factorial is the number of ways mixing these elements. And then we have to mix the other ones. So that will be n minus k factorial. So we know that the number of such pairs is exactly this number. So now try to fix the cyclic permutation. So we are now here, and we consider the members of f which are intervals in this cyclic ordering. And we cannot tell how many of the members f will be intervals here, but we know that we cannot have more than k because they are intersecting also. So because the f's are intersecting, then their maps here are also intersecting, and by the lemma we know that it cannot be more than k. And so first I write the number of cyclic permutations. And so k is the largest value. So typically for a G, for one cyclic permutation, we have a number which is at less than or equal to k. So if we write k here, then we get an inequality. And so what we obtained is n minus 1 factorial over, we can divide by k, so we get k minus 1 factorial and minus k factorial, and this is really m minus 1 choose k minus 1. Question? So, yeah, this is definitely shorter than the original proof, but this transformation, this shift is very important, and there are deeper theorems, more difficult theorems where you cannot do anything with this method, but using the shift you can get many more results. But now I want to show you some other situations where the cyclic method of cyclic permutations is useful. I don't know, I call it a proposition. Yeah, young people typically don't distinguish between proposition and lemma, and so I think the best way to distinguish is when proposition is when it's very easy to prove, but it's going along the main line. So it's an important result in the theory. Then it's but easy to prove. That's the proposition. A lemma is like this one. Then it somehow it's different. It doesn't say anything about real families of subsets. So yeah. So proposition is that I write it very shortly in Sperner's theorem. The only extremal families are actually we have seen that this is true for the case when n is even, because this pushing to the middle, it always increased the number of sets. That is strictly increased, so we arrived to this one. But in this case, it was a so we were able to go to these two levels, but we didn't know about between the two levels. So the only situation could have happened that some of these and some of these. And now I proved that this is not possible. Again, we take these pairs. Yeah, C is a cyclic permutation. I don't write it down again. But so F, yeah, so F is the family. Satisfying the Sperner. And F is in the family, and it's an interval along C. So we do the same thing again, that we mix the elements in a cyclic way, and we consider those members of the family which become an interval here. Yeah, this looked easy in the previous case, and this is true again, basically the same, just we have to write now f factorial, that because the sizes are different. So this is the number of pairs, because yeah, So the same calculation works. So we fix the interval, and then we mix the elements within F and outside F. But now, again, the number of secret permutations is n minus 1 factorial. But what can we say about the maximum of the numbers of intervals along the cycle? Now, I asked the audience, so what is the maximum number? Of course, Sperner property has to be satisfied. So no subset is a subset of the other one.
One more time, please, your question.
So along the cycle, we have intervals of different lengths. And no one is contained in another one as a subset. What is the maximum number of such subsets? So the Sperner theorem asked for the cycle. Little help. So I consider two sets starting from the same point. Can we have both of them? No, because this is a subset of this one. So we can have only one set for every point. So we cannot have more than n. And can we have n sets? All sets of the same size. They are good for any k, all k element subsets, except 0 and n, because there is only one. So we have n. And this inequality So what did we get here? We so this is n factorial, and we divide this by this side. Then sorry, no, we have to sum these because it depends on the sizes here. So so this side is okay. So this was wrong here. This f. I'm sorry, because so when we fix one f, then we get different numbers. So it's a sum. So this is an error here. So this is the correct one. So for every f, we calculate how many cyclic permutations are there, where f is an interval. And now what we obtained, dividing by n factorial, we obtain some you can check it. It's correct. So we divide it here by n factorial, we get 1, and here we have the reciprocal value of n choose f size. And so from here, we can get again, so this is, we have proved this actually before, the YBLM inequality, or LYM if you prefer. So we have this inequality if we replace every term by the smallest one, which means when this is the largest, so the middle one. And then we obtain that f is at most this one. So now you can say, oh, we didn't get anything new. We proved the same thing as in the Lubel's proof. But now we are able to determine the extremal families. Namely, we follow where we have equality. So here at that point, we have equality if we have n here for every f. So I recall we fixed an f. I'm sorry, no. Fix a cyclic permutation, not an f. A cyclic permutation, and we know that we cannot have more than n intervals along the cyclic permutation. And this was a maximum, but we have in a strict equality here only if we have n sets. So if then we must have exactly n intervals for every C. So now so it means that we need a set starting from every point, because there are n points, and we have seen that from one point we cannot have two, because then one will be a subset of the other one. So let if bi is the interval starting from I. So name them. So this is I, and this is BI. Of course, here we always mix the element, but for the moment we suppose that they are indexed from 1 to n. It doesn't make any difference, just it would be very complicated to use many indices. So what can we say about the size of BI and BI plus 1? I need an inequality. I don't hear it.
BI is at least BI plus 1?
The same, you said?
No.
No, I didn't hear the crucial word.
At least.
At least, yeah. Yeah. So if this is BI, and BI plus 1 starts from here. If it's 1 less, then so this is less than this one, only 1, already this will be a subset of the other one. So it means that it has to be at least this much. Yeah, I didn't finish the lemma. I started the proof, but now I can finish the statement. And yeah, so here I should have written from 1 to n. So that's very important that we have n such sets exactly. And then so this is the statement that they all have the same size. Why? Because we can continue this to be n, because it's same is true at every step, but it's also true for Bn, that Bn should be less than B1, because otherwise if Bn is B1 is shorter than Bn is going like that, and B1 is shorter by 1, then it will be a subset. And we started from B1, and so you can see that this implies that they are all the same. So we have proved something stronger, that even in this inequality we can have equality, exact equality, only if they all have the same size. So oh, I didn't finish yet. I'm sorry. No, I'm too fast. So now we know that they are all equal along one cyclic permutation, but for different ones we could have a different size. So by the lemma we know that they are equal, but we take another cyclic permutation, then they can be different. So there are 5, and the other one all the 10 element sets. So we have to prove that, so this is lemma 1, lemma 2, is that if C1 and C2 are two cyclic permutations, then the members being intervals in them are have then all of them have the same size. So for one we know that they have the same size. For this one we also know, I'm sorry, telephone. So for the other one we also have the same size, but we don't know if they are the same, these constants. And take so take any two I didn't formulate it very well. So when we have f, it is true, but I will prove something different. So we have two members. So now this is a C. This is a C, and suppose that two members are in this cyclic permutation. They have yeah. So we have this one, and take such a C that F1 and F2 are intervals. It's easy to do. We just fix the intersection. So this is the intersection, and okay, once more. So this will be the intersection. This will be F1 minus F2, this part, and this part is F2 minus F1. So we order the elements in this way. So two sets, intersection, and all these things are defined in the original set. And then we order them, we start the cyclic permutation in this way. And then the rest is not important. And we know that the sets along this permutation, cyclic permutation, what we obtained in this way, all the intervals have the same size. And this is one cyclic permutation, and we have two intervals from a family. So we obtain from this lemma, we obtain that they must be of the same size. So now I arrived to this point really. So this equality here, in this inequality, if we have equality, exact equality, then it means that all f's have the same size. So, and then if we want to get equality here also, then we must have that f is either this one, so this common f is either this one or that one. If you take a different value, then it will be different here. So this is the case. Yeah. So in the case of even, I have told that we don't need a proof, but it works also here. That if you have here exactly n½ then you must have all f's to have the same size also. Now I show you another proof using this idea with a little bit spiced. So you understand that the sets are, any two sets are intersecting, the intersection is non-empty, and no one is a subset of the other one. So first we excluded this one, in second we excluded this one, and now we exclude both of them. Any suggestion? n choose n half is you take all n half element sets, then you will get disjoint ones. But then you don't use all the elements. That will be too small. Yeah, the two cases they are, but you can formulate it in one statement in even or odd case. About so the first one, which is more than half. And this can be expressed in this way. So when n is even, then it means n half plus 1. And since they have the same size, this cannot happen. And because they are too big, this cannot happen either. And if n is odd, then again, because the sum of two such things is more than n. And of course, this is sharp, because if you take these sets, then they will satisfy the conditions. And so the new trick is now we need again a lemma for the cycle, but first I show you what no, I start with the lemma. So C cyclic permutation and yeah, so I have is the family, but now the double counting will be somewhat different with a weight. So and I have to improve my memory. So so if we have B1, B2, BR intervals in C, but of course they are all in the family, but here so it's intersecting, so this is sorry, and it's better to write here intersecting Sperner. So the same condition as in the theorem we have for the intervals, but we need names this time because it's more complicated. So we take write in this stupid way. So what I mean, we take double counting, where instead of what, so for every pair C, B, we, in the previous proofs, we took only one. And here for every pair, we add a weight function, a weight, and this will be the weight. So basically the same thing, the double counting, but with a weight. And so the lemma claims that this is at most this much. So can we have this much? Yes, if we take all sets of this size, so same size, again they will form an intersecting Sperner. Actually, some people say Sperner in an English way, but I think the right way is to call everybody by his real original pronunciation, and he was German. So in German, SP, when it starts with S and continues with P, then you pronounce it sh, not s. Of course, my pronunciation is not real German, it's the Hungarian approximation. Okay, so you see, when R is n, and we have all sets of this size, then all of these terms will be equal to this one, and since this is n, we have equality, so we can reach this. So we have to prove that we cannot have more than this. So we have to distinguish two cases here. When R is equal to n. So then we know that 1b, we have a b starting from every point. They might be of different sizes, but we just proved before that all B's have the same size. So it means that the sum will be n choose k So this is the sum on the right-hand side, or sorry, left-hand side. And we have n terms, and so we take this to be the maximum. So if one thing I forgot. So the maximum could be, okay, I write it here first. So if n is even, we obtain this one. But this is impossible, because if k is n half, then we have these two sets. We must have a set starting from every point. So we have these two, which are disjoint. So this cannot be. So k cannot be n half. And then we take the second largest value of n choose k, and when n is even, then is it still there? Yeah. Then this is the second largest one, and if n is odd, then we can take the largest one. But this case is somewhat different when r is not equal to n. Then we cannot say that they have the same size. But we can try to maximize these weights. So the best thing would be to take n half everywhere. But as I mentioned here, this is impossible. That sorry. It's impossible to have too many of them. So n half elements, sets along the cycle, how many we can have? N half. Yeah. So containing this point, they are okay. And so because for every pair, every such pair, we can have only one. So you order them by pairs, and you can have at most one out of each pair. So we can have this many of the largest possible. And the rest, which is n r minus n half, is smaller. Oh, I forgot to tell you before that the whole theorem is trivial when n is odd, because already the Sperner property says this, that you cannot have more in the family than n choose this number. So we have to consider only the even case. And this is why I wrote here n half. So we have r members are terms here, so the other ones can be a little bit less. Here I could have written -1 is the same thing, but because of the result, it looks better to write 1. So this is the second best. And take the largest possible value for R. Because yeah, I understand. You also understand why we cannot have more for this, why we cannot have more than this one. Because if it's equal, R, this is n, then R is, I'm sorry, if this is n½ then R is n. And this was the previous case. So n is less than less than equal to n-1. So the largest value is n-1 minus n½ this. And it's easy calculation that this is n. It's elementary calculation that these are equal. So now we proved the lemma only, and now we do the double counting really. So now I go back to B is okay. So now we no, because B was only along the cycle, and here we have members of the original family. So I don't see why I have indices here. So this is what I was telling earlier, that we make the double counting with the weight. So we take this sum for every such pair where C is a cyclic permutation, F is from the family, and C is and is an interval. Along C. So we do the same thing as before, that CF and choose F. We can do in two different ways the sum. So we, I like this order here. Yeah. So in this case, the double counting means that we take two different orders of the summation. So this one here, C is fixed. Then no, I better start with this. I'm sorry. This is where no. Yeah. This is the one. Okay. Sorry. So first we think that F is fixed. And then take this sum. This sum is just trivial because this number is the same for every term. We just have to calculate how many cyclic permutations are there, how many times we take this. And this is like before, it is and summing for F. And so what happens if we take this one? So now C is fixed. Then we have this sum. And so the set F's are intersecting Sperner family along a given cycle. So we can use the lemma that this can be replaced by n times n choose Of course, now we have to multiply this by n minus 1 factorial. Something is not clear. This is good. Sorry?
On the right, you shouldn't have all the permutations.
Yes.
Only this contains F as interval.
Sorry?
Only this permutation that contains F.
Yes. Yes, yes, yes. So when so this is wrong here. Because now we fixed, I wrote here F is fixed, but I didn't use it. So we don't have all m minus 1 factorial ones. We did many times how many cyclic permutations we have where F is an interval. That was F factorial times n minus F factorial. And this is sum for F, and this cancels out. So we get n factorial. And so since it's a constant, we have size of F times n factorial. So I repeat what we obtained. So this is n factorial here times so when I wrote it here, I should have deleted the sum. So n choose n plus 1 ceiling. So this is the left-hand side, and the right-hand side is and well, again a sum. We don't need the sum. I am writing nonsense. So we don't have any sum, right? Because so this was the maximum of this sum, and then this many times we had to take this, and so we obtained n factorial here, and this was n factorial times f, and so we obtained that f is at most this one. So I have 10 minutes. 12. I wanted to tell much more. I think I tell you only a result without proof, of course. So you remember when F consisted of k element subsets, then we defined the shadow. K minus 1 element subsets deleting 1, 1, 1 element from each member. So this was the shadow. And so we have seen that the shadow is I repeat the proof because there are some people who were not here in the first class. So for each member, each k element set, we can delete one element in k different ways. But in this way, we can obtain the same k minus 1 element set in many times. At most, how many times? As many times we have an element outside. Because so if the k element set is this one plus a point, then we obtain this one. And this number is m minus k plus 1. And So now I want to show you that this was useful in Sperner's original theorem, but it's too weak. It's very, very weak. Because if k is fixed and n tends to infinity, then it tends to 0 for given f and given size of sets and given k, which is you can see that it cannot be true. To have a feeling, try to think about the case k equals 2. So what is the question is minimum of the shadow when n is given, k is given, and the size of f. So we know how many sets we have. This is now the question. And we have this lower bound, but this is not good. This is what I claim. So what do you think if k is 2? So we have actually a graph. We know the number of edges. And the shadow is the non-isolated points, because you delete one endpoint of each edge. So the non-isolated points. So try to think a second what could be the best in this case. So we want to minimize the number of isolated points in a graph when we know the edges, number of edges.
Square root of 2f.
Sorry?
Square root of 2f.
Yes, it's kind of true, but so it's a the construction I wanted to hear. So it's a complete graph, and you didn't say the complete graph, because if the number of edges is not in the form a choose 2, then we cannot do it. But so when 4 edges we can do this, but 5 edges, 6 edges, this is the minimum. And then we continue in this way. So between two complete graphs, we can make an almost complete graph when this is not n choose 2. And we can imitate this when the size of f is equal to a choose k. So it's a nice number. Then so you take an A element set and all K element subsets, and then deleting the elements one by one, you get all K minus 1 element sets. So you can construct this, and this is true, that you cannot have a smaller number than this one. But what happens if we are not so lucky? integers so then there is a unique expansion of M of this form. So it's kind of homework for when you study binomial coefficients. Probably it's the first year. So you can prove. So what are we trying to do? That if we are not so lucky that something choose K, then start with this, and we do the same thing with the rest. So this is the remaining, and then we take a new point here and take those K element sets which have K minus 1 here and this one. And then this gives, you take a subset here, and you take, so this, the original size was AK, and this subset has size K minus 1, AK minus 1, and you take all K minus 1 element sets plus this one. So this is why we have, and these conditions are needed to have unicity. So, and then, so this is the shadow theorem. If so, I denote it by M because I have this expansion. Then sigma F is at least AK choose K minus 1 plus AK minus 1 choose K minus 2 plus AT choose T minus 1. So from this we made this one, and we do the same thing with the whole sum, that we decrease the lower part everywhere. And this is what I will not prove in 50 seconds. So actually, people are still trying shorter and shorter proofs to find shorter proofs, but even the shortest one is not easy. So thank you.